In section 11.2, we're going to be conducting inference on two groups, but this time it's going to be for dependent, aka matched pairs data sets. So when you think of that, remember, those are the ones that are one group measured twice. So if you think of pre and post test, or a before and after, or people that are relatives of each other, that are not independent of each other. I just wrote that down. Those would be dependent groups. Now you can see that it's very similar to previous hypothesis tests we've done, but it's a little bit simpler than the one we were doing in 11.1. And we'll explain why that is in a second. But the key here is that you're doing it for a matched pairs design, and it's for the difference. All right, so we'll have a simple random sample. We need a dependent sample right there, which is this bit that I said above. One group measured twice, and that's the new part. That's the part we did not have back in chapter 10 and 9 when we were doing this before. So that's new. But the sampling independent of the population, where if you're sampling without replacement, you need little n to be less than 0.05 capital N, sample size and population size respectively, and that you need either n to be bigger than 30, or you need a graph that shows that your data set is normal with no outliers. So those three pieces, the first, the third, and the fourth, we've actually seen those before. And then the dependent sampling we saw in section 11.1. It's the matched pairs group. And then you can see you have to choose your hypotheses, you have to write out your formula, and I didn't write just use calculator on this one. That's because this one's not actually that difficult to do. We can do this. Now you see a lot of D's and right, SD, D bar, and mu D. So I guess we could make a little note somewhere along the way. I'll write it over here. D stands for difference. And we'll see why that is in a second. So when you see mu D, that's the mean of the differences. It's the population mean, actually, of the differences. D bar is the sample mean of the differences. I'm just going to put quotes for differences. Actually, I'll put DIFF. There we go. All right. And then SD is the standard deviation of the differences. So we're going to do this a little bit differently than we've done for section 11.1. So we're going to have to find differences. And we find differences first, and then we conduct the test on that. So this is going to work a little bit differently. But the rest of it kind of is the same thing we've seen. As a matter of fact, this is very similar to what we saw back in section 11 or 10.3, and it is extremely similar. But you'll notice that the hypotheses, as in all of chapter 11, always assume that there's no change, that there's no difference. So the null hypothesis is always that there's no difference between the two groups, no change, right? No significant difference for all of them. So the hypotheses are actually easier to calculate in chapter 11 than they were in chapter 10. And then we have our standard draw pictures, but these are with t-values, of course, because this is for a mean, not for proportions. Proportions use z, but means use t. And then we reject if our p-value is low, and we state our conclusion. All right, so let's start working on a problem that puts all this together. A study was carried out to determine whether Reiki touch therapy, or is it Reiki? Sorry, I don't know how to pronounce that, was useful in the reduction of mean pain level in chronic pain sufferers, including patients. The pain level reported by a random sample of 13 patients before and after. See that? Before and after. That's why this is a dependent sample. That's the answer to the first question. So you're doing the pain level before and the pain level after this therapy. This touch therapy, sort of massage, I imagine. We're going to use the results to determine whether there was a reduction in pain level after the Reiki therapy. All right, so for the first part, why is this a dependent sample? We would say it's because it's one group of patients. These are chronic pain sufferers, right? Measured before and after. right? Before and after is classic dependent sampling. All right, great. So now we're going to find the differences for each patient. Now, of course, this is actually a pretty easy calculation to do. 6 take away 3 is 3, 2 take away 1 is 1, and so on. But I also want to show us how to do this on StatCrunch as well as the calculator. So let me grab the calculator first. So let me clear this out. So stat, edit. And I'm going to clear out my old data. And again, this isn't for this particular problem so much because we know how this problem is going to work. So we have pain levels of 6, 2, 2, 3, 3. Right, so we enter all the values for the before. So all the values for before go in L1, and then all the values for after go in L2. And we would do the same thing, oops, except we would not mess up. That's because I'm typing so fast, it doesn't like it. All right, so this is wrong. I've done something wrong because they don't line up. They need to line up, right? Because there's 13 patients, there have to be 13 scores. And I found it. I was missing a 0 right there, so I put that in there. And now we're all set. All right, now, why am I having us do this? Because this is a really easy problem. Well, yes, but other problems would have maybe more decimal places or be a little bit trickier. So what you can do is you can put your values for before in L1, and I'll actually label that. So that goes in L1, this goes in L2. Only if you're using the calculator, of course. And then here for L3, what you can do is go up and press, well, we want to do before minus after, if you see this right here. So it says it wants before minus after. Here's before, here's after, right? So I want L1 minus L2. Okay, so if I have L1 minus L2, I can actually type that into the calculator and have it do the calculations for me. So I can say, hey, take that first list, second 1, which is L1, it's in blue above your number 1, minus second 2. You have to do it up at the top. Make sure you're highlighting the L3. And then if I press enter, poof, all the values are found. So I can see that it's 3, 1, 2, 3, and so on. All right, now you can also do this in StatCrunch, so let me go show us that as well. Oh, real quickly, in case you're interested, you can actually do it in Desmos as well, if you're wanting to. I would just type, these are the patient numbers over here, but then I would type my pain levels before, my pain levels after in a table, and you just click on the next column over, and you type Y2, or my Y1 minus Y2, because we wanted before minus after. There they are there. Just a minor point in case you wanted to use Desmos rather than a TI-84. So here we are in StatCrunch rather than Desmos. And of course, this particular problem is not exactly difficult to do. But again, we're just doing this to be able to learn how to do this for other types of problems that are more difficult, that have more decimal places. All right, so it took me a minute to find it. We need to compute an expression. So you go to data, you go to compute expression, and we just go build it. We could actually probably type it in there as well. But all you want is before minus, so I press the subtraction button, after. And then say OK. And then that's what we wanted, before minus after. So I should be able to click compute. And there they are, before minus after. Simple as that. And if you wanted to, you could call it something. We could call it differences, because that's what it is, right? And those are all the same values that the calculator and Desmos found. Now, why am I doing all of this? Like, this seems like a lot of work. And it is. It's not much, actually. It wasn't too bad. And it's helpful, especially if there's tons of decimals in here and really ugly numbers. It'll find all those numbers really nicely for us. But the other reason we need it is these are the differences. So if you see right here, it says differences. And we need those to find these values over here, because that's the mean of the differences, and that's the standard deviation of the differences. So this is D, right? The D that you're doing these calculations for. You need the mean, right? And you need the standard deviation. Actually, I'm going to change my arrow. I'm just going to put a big arrow here, and that way I can write mean is actually the sample mean of the differences, those D's, and this is the standard deviation of the differences. Of course, it's the sample standard deviation. So these are the D's here, right? Differences that you're finding. Okay, so back to chapter 3, right? We need to be able to find the mean and the standard deviation of those differences. So you go to stat, calculate one variable stat, remember this? But your list is L3. Your list is where the differences are, right? Which is list 3. So you say second 3, and then go down to calculate and press enter. And the D bar is that X bar at the top. It's 1.92, actually I'm going to do this in green, 1.923, and the standard deviation was 1.605. And of course, if you want StatCrunch instead, which many of you do, then you would do stat, summary stat, columns, right? Remember chapter 3? It was a while ago. And you'd say, on those differences, I want you to find me the mean and the standard deviation. And if you want, you can find me the n as well, but there we have it. The mean and the standard deviation, 1.923 and 1.605. And n was 13, but we knew that anyway because we could see there's 13 patients here. If you want, you can write patients just to help you understand, right? 1, 2, 3. I know it looks like there's a lot more numbers than 13, and there are, but there's only 13 individual patients. These are their pain levels before, these are their pain levels after, and this is the difference between the two. All right, now suppose we want to conduct a test of whether there has been a mean reduction in pain level after the Reiki therapy using a 0.05 level of significance. Keeping in mind that we found the differences, what should be our hypotheses? Okay, so we're not actually doing the whole test here, obviously, because there's not enough space. But what would we do to make those hypotheses? Well, we know automatically that because this is a matched pairs, it's always going to be mu d, and we know it's going to be equal to 0. Period, the end. Done. Right? So then the question is, what is the direction that we think this other value is going to go? Because we know it's going to be 0 for both. Right? Because we can see that when we look at these. They always have 0. They always have equals for the 0 hypothesis, the null hypothesis. So then it's just a question, is it less than, is it greater than, or is it not equal to? Well, we know it's not equal to because they're talking about a reduction in pain level, right? So is there a significant reduction in pain, reducing of pain? Okay, so let's see here. Let me write it with the other way to think about this. So if I want before to be greater than after, right? That's a reduction in pain, right? It was greater before than it was after. So then the differences we did were before minus after. So if I took before minus after, that would be greater than 0, right? Because if I subtract after from both sides, that would be this. And you can see right here, this is D, before minus after. That's D. We did it right here. D is L1 minus L2. And that means that I want it to go this way, right? Because I want this symbol right here. I want after to be less than before. So the reduction, the word reduction, doesn't necessarily mean it's less than. Reduction means that, in this case, the after is smaller than the before, right? So this is why that is. Sneaky, huh? You got to watch out in chapter 11. Sometimes they'll go the opposite way from which way you think, because normally you'd see the word reduce and you think making it less than, but it is less than. It's the after is less than. The pointy end's pointing towards after. And that actually made it a greater than symbol overall for the problem. All right, now let's look a little review. Now we reviewed chapter 3 right here with finding sample mean and sample standard deviation. That was fun. Now let's remind ourselves about box plots, right? This is the pain level for the patients before, right? So these are their minimum, their quartile 1, the median, the quartile 3, and the max, right? Remember those? It was a long time ago, I know. All right, so here, this is Q1, this is median, this is Q3, right? This is the max, and this was the min down here. And then we go to after the therapy. So there's the max right here still, but Q3 is down here, which look, that's below the median from the before. There's the median, there's the Q1, there's the min down there. So the question is, what do we expect to show? Well, we expect to show that after is lower than the before, that there is a reduction in pain, because this pain level, I mean, granted, the max is still where the max was, but the pain level overall is quite a bit lower. Q3 is lower than that median. So we expect to show or to support the claim that the Reiki therapy reduces pain. And you can see it because the after box is significantly lower than the before. How is it lower? Well, it's Q3 of the after is lower than the median of the before. For another thing, the median of the after is lower than the minimum. Look at that. Half of the patients are below the minimum score from before. That's another way you can see it. Now, this is a review of box plots, but it's also trying to give us a sense of what we think we're arguing for. We think we're going to be showing, more or less, that this Reiki therapy is reducing pain, because we can see that this box is significantly lower in all of its aspects than the box was before. So we think overall, for most patients, this is going to have a benefit, going to have a reduction in pain. That's what we think we'll end up proving, quote unquote, proving with an hypothesis test. But this video is getting long, so we'll have to do that in the next video.